Did you get the same answer I did? 900,000 joules. We know we have 215 kilocalories. There's 1,000 calories in a kilocalorie. And 4.184 joules is 1 calorie. So the calculator says 899,560 joules. But we only have 3 sig figs in our kilocalories, so I have to round, and I need 3 sig figs. When I round these 9s up to 0, I have to somehow show that those 2 trailing zeros are significant, but the last 3 are not. So the easiest way is to draw a straight line over those 2 zeros that are significant. 900,000 joules. You could also put it in scientific notation, or converting it to kilojoules. It's easier then to just put that decimal point. But the question said show it in joules. So those are just some quick review of actually what a joule is. Now, as we go through, we're going to talk about energy in a lot of different kinds of situations. We're going to talk about energy required to perform a chemical reaction. We're going to talk about energy absorbed and energy released as we try and heat and cool things. So in this chapter, we talk about the state of a system. And we talk about state functions, which are functions that relate to what situation we have right now. We talk about the state of a system. If we think of our system as this room, I could say, well, the barometric pressure in this room is whatever it is, and the temperature is this. So for us in chemistry, pressure, temperature, volume, and composition tell us what the state of a system is. And the important thing about a state function, it depends on what it is now, not how it got there. So if we're talking about the temperature of this room, it doesn't matter that early this morning it was very cold in this room and then they turned the heat on. We're just looking at what the temperature is now. We don't care what it was earlier. So when we talk about these functions, we talk about energy as a state function. And the total energy is defined as the letter uppercase U. It's the internal energy, and that comes from the kinetic energy, the energy of motion, and the potential energy, which is stored energy, of which chemical energy is one type. And we can't measure the total energy because it takes energy or causes an energy change to make energy. So we focus on measuring energy changes, delta U, because the Greek letter delta means change. That's why you came to Delta College, to change your life, right? So delta U is the final energy minus the initial energy, which for us in chemistry, the change in U is the change in the energy of the products minus the energy of the reactants. So that's a definition we're going to use in a few minutes. We also talk about work as a type of energy. And for us in chemistry and in physics work, we think of a force moving something through a distance. So we have the change in energy, U, is equal to Q, which is the heat energy, plus W, the work energy. Now, this section is very, very important when you describe these numbers because you have to know these definitions. When we talk about the definitions, Q is the heat absorbed by the system, and W is the work that's done on the system. Both of these can be positive or negative because we talk about positive and negative numbers for energy. When energy is released, we say that it is exothermic because energy is exiting the system. When it takes energy, well, actually heat. When it takes heat to make these equation go, then the system has a positive heat, and so it's endothermic. So we use exo and endo to say heat going out or energy going out is exothermic or exergonic, and energy or heat coming in is endothermic or endergonic. So it's important to think about which way these go, and you'll have to know this in order to successfully do the problems. So when heat is positive, and it's a plus, heat is absorbed by the system, it's endothermic. When heat is negative, we have a negative sign, heat is released, it's exothermic. When we define work as positive, work is done on the system by the surroundings. And when work is negative, work is done by the system. Those are the key words that you have to recognize when you're reading a problem so you can do this properly. Let's look at an example. Calculate the change in total energy for a system that releases 1.34 times 10 to the fourth kilojoules of heat and does 2.98 times 10 to the fourth kilojoules of work on the surroundings. Well, we know that delta U, the energy change, is equal to Q plus W. Now we have to read carefully to find out what these numbers are, what their signs are. If the system releases heat, what is the sign for the heat? It's Q, but is it negative or positive? It's going to be negative, negative heat. So the system does work on the surroundings. So is that going to be positive or negative based on those definitions? It's going to be negative because the work is done by the system. So it's negative. So delta U is equal to negative the heat, 1.34 times 10 to the fourth kilojoules, plus negative the work, negative 2.98, negative 2.98, not 29.8, times 10 to the fourth kilojoules. So delta U is negative 4.32 times 10 to the fourth kilojoules. So for these, the math is as simple as adding two numbers. The difficult part there is recognizing whether the signs on those numbers are positive or negative. Go ahead and try this one at your seats.